Steel wheels, steel rails, thousands of tons of weight, and yet trains move across countries at high speed without slipping, sliding, or falling off the track. It looks simple when a train passes by, just metal wheels rolling along metal rails. But hidden inside that simple motion is one of the most elegant pieces of engineering ever created. A modern train can weigh more than 1,000 tons. It can move faster than 300 kilometers per hour. It can carry hundreds of people or massive loads of cargo. And still, those narrow rails guide it perfectly for thousands of kilometers. No steering wheel, no driver turning left or right like in a car. No visible system holding the wheels in place. At first glance, it almost feels impossible. A tiny mistake in balance could send such a massive machine off the rails. Yet that rarely happens. Trains have been running safely for nearly 200 years, and the reason behind this stability is far more fascinating than most people realize. Many people believe the answer is simple. They think the wheels are locked tightly onto the track, almost like a toy train that cannot move sideways. Others believe the small lip on the inside of the wheel is what holds everything in place. That little edge is called the flange, and it certainly looks like it is doing all the work. But the surprising truth is that the flange is not what normally keeps the train on the track. Most of the time, it does not even touch the rail at all. The real reason trains stay perfectly balanced is hidden in a small and brilliant detail of the wheel design, a detail that most passengers never notice. This tiny design choice allows a massive train to guide itself automatically. No sensors, no computers, no complicated steering system, just pure physics and clever engineering working together every second the train moves. Even more surprising, the system constantly corrects itself. If a train shifts slightly to one side, the wheels quietly guide it back to the center. If it drifts the other way, the same invisible force pushes it back again. The train is always adjusting, always balancing, always staying perfectly aligned with the rails. All of this happens silently beneath the cars, while passengers sit comfortably inside, unaware that a simple geometric trick is controlling the motion of one of the heaviest machines humans have ever built. This design was discovered in the early days of railroads, when engineers were still learning how steel wheels behaved on steel tracks. They realized that forcing the train to stay in place was not the smartest solution. Instead, they created a system that allows the train to guide itself naturally. The result is a perfect example of engineering elegance. A solution so simple that it almost feels obvious once it is understood, yet so powerful that it has been used for nearly 2 centuries across millions of kilometers of railway lines around the world. Every time a train moves through a curve, every time it speeds across a straight track, and every time it travels hundreds of kilometers without leaving the rails, this hidden system is quietly doing its job. The most interesting part is that this idea does not rely on strength alone. It relies on balance, geometry, and motion. The wheels are shaped in a way that creates a natural correction mechanism. When the train shifts even slightly, the physics of the wheel and rail interaction gently push it back into position. This means the train is not being forced to stay on the track. It chooses the center of the track automatically. This small detail makes rail transport one of the most efficient and stable transportation systems ever invented. Without it, modern railways might not even exist. In this video, the mystery behind train stability will be uncovered step by step. The real reason trains stay on the track will become clear. The hidden design of the wheels will be explained. The role of the flange will finally make sense. And the physics that allows a 1,000-ton machine to balance perfectly on narrow rails will be revealed in a way that is simple and easy to understand. Along the way, some lesser-known facts about train engineering will appear, including why the wheel shape is slightly different from what most people expect, and why this difference quietly controls the movement of an entire train. By the end of this video, the next time a train passes by, it will look completely different. What once seemed ordinary will suddenly reveal a clever system of balance and motion that has been hiding in plain sight.
the rails will no longer look like simple metal bars on the ground. They will look like part of a perfectly designed guiding system that has shaped global transportation for nearly 2 centuries. Stay with this video until the end, because the final explanation brings together all the pieces of the puzzle and reveals the simple but powerful physics that keeps trains safely on track every single day. Welcome to Feynman's chalkboard, a place where the hidden science behind everyday things becomes clear and fascinating. If discovering the physics behind the world sparks your curiosity, make sure to subscribe and join this journey into the ideas that quietly shape the way our world works.
Movement on a road usually depends on control. A car stays on its path because the driver constantly adjusts the steering wheel. Even a small turn of the wheel changes the direction of the tires, and the vehicle follows that direction. Buses, trucks, and motorcycles all work in the same way. Their tires can rotate freely and point in different directions depending on how the driver steers. This constant control keeps the vehicle safely on the road. The road itself does not guide the car. It only provides a surface to drive on. The driver is always making small corrections to keep the vehicle moving where it should go. Without that steering control, a car would slowly drift away from its lane or leave the road entirely. Trains operate in a completely different way. A train driver cannot steer the train left or right like a car driver. Inside the locomotive, there is no steering wheel that turns the wheels. The driver controls speed, braking, and power, but the direction of the train is already decided by the rails beneath it. When a train enters a curve, the driver does not turn the wheels to follow the track. The rails themselves guide the train through the turn. This creates an interesting question. If there is no steering system, what keeps the train centered on the rails while it moves forward at high speed? Many people believe the answer is very simple. They think the wheels are tightly locked onto the rails so they cannot move sideways at all. According to this idea, the train is trapped between the rails in a way that makes falling off almost impossible. It feels logical at first because the rails look narrow and the wheels appear to sit directly on top of them. From a distance, it almost looks like the train is sliding along a fixed path that it cannot escape. This belief leads to another common assumption, that the small edge on the inside of the wheel is constantly holding the train in place. This small edge is called the flange. When someone looks closely at a train wheel, the flange stands out immediately. It is a raised rim on the inside of the wheel that curves downward beside the rail. Because of its position, many people think it presses against the rail all the time and physically holds the train on the track. The idea seems convincing because the flange looks like a barrier that blocks the wheel from slipping off the rail. It appears to act like a guardrail attached directly to the wheel. But the reality is far more interesting than this simple explanation. During normal movement, the flange usually does not touch the rail at all. The wheel rolls smoothly along the top surface of the rail without the flange making contact. The space between the flange and the rail is actually intentional. Engineers designed it this way so the wheel can move slightly from side to side without friction from the flange. If the flange were constantly pressing against the rail, it would create enormous wear and resistance. The wheels and rails would grind against each other every second the train moved, which would quickly damage both parts and waste a large amount of energy. Instead, the train moves along the track with the flanges floating just beside the rails, ready to act only if something pushes the wheel too far to one side. This means the real system keeping the train centered must be something else entirely. The answer lies in the shape of the wheel itself, a detail that often goes unnoticed because it is subtle and easy to overlook. At first glance, train wheels appear flat like the tires on a car, but when examined closely, they are actually slightly angled. The surface of the wheel is shaped like a very shallow cone. This means the part of the wheel closer to the flange has a slightly larger diameter than the part farther away from it. The difference is small, but it is enough to create a powerful effect when the wheel rolls along the rail. Both wheels on a train axle are fixed together on the same solid axle. This means they always rotate at exactly the same speed. They cannot spin independently like the wheels on a car. When one wheel turns, the other wheel must turn at the same rate because they are physically connected by the axle. This detail becomes extremely important once the train begins to shift slightly to one side of the track. When the train is perfectly centered, each wheel touches the rail at the same point along its conical surface. Because the contact points are equal, both wheels effectively have the same diameter at the point where they touch the rail. Since they rotate together at the same speed, the train moves forward in a straight line without drifting left or right. But trains do not stay perfectly centered all the time. Small movements happen constantly as the train travels. Vibrations, wind, uneven track surfaces, or tiny shifts in weight can move the wheels slightly toward one side. This is where the conical shape of the wheels begins to do its quiet work. If the train drifts slightly to the left wheel moves toward the narrower part of its cone, while the right wheel moves toward the wider part. Because of this shift, the right wheel now has a slightly larger effective diameter than the left wheel. Both wheels still rotate at the same speed because they share the same axle, but the larger wheel covers more distance with each rotation than the smaller wheel. This difference in distance creates a gentle turning motion. The side with the larger diameter wheel begins to travel farther, causing the train to curve slightly back toward the center of the track. The moment the train returns closer to the middle, the contact points on both wheels become equal again, and the system balances itself once more. The same process works in reverse. If the train shifts to the right wheel moves toward the narrower part of its cone, while the left wheel touches the wider part. Now the left wheel effectively becomes larger. Because it travels farther with each rotation, it slowly guides the train back toward the center of the track. The entire system operates automatically with no human control and no electronic sensors. This design creates a natural, self-correcting motion. The train constantly adjusts its position using the geometry of the wheels alone. Even small side movements are corrected smoothly and quietly as the train rolls forward. The passengers inside the train rarely feel these adjustments because they happen gradually and continuously. The brilliance of this system becomes even clearer when a train enters a curve in the track. In a curve, the outer rail is longer than the inner rail. If both wheels had exactly the same diameter at all times, one wheel would have to slip or slide to match the difference in distance. Sliding creates friction and wear, which engineers try to avoid whenever possible. The conical wheel shape solves this problem elegantly. When the train enters a curve, it naturally shifts slightly toward the outer rail. This movement places the outer wheel on a slightly larger diameter part of its cone, and the inner wheel on a smaller diameter part. The outer wheel therefore travels a greater distance with each rotation, perfectly matching the longer outer rail of the curve. At the same time, the inner wheel travels a shorter distance, matching the shorter inner rail. The result is a smooth curve with minimal slipping. The wheels roll through the turn while automatically adjusting their effective diameters to match the track. This allows the train to handle curves efficiently, even though both wheels are locked together on the same axle. The flange still plays an important role, but it is more like a safety backup than a guiding system. When the train takes a very sharp turn, or when strong forces push the wheels too far to one side, the flange finally touches the rail. This contact prevents the wheel from climbing over the rail and leaving the track. It acts as a final protective barrier that keeps the wheel safely aligned. Because the flange touches the rail only occasionally, it experiences far less wear than it would if it were constantly rubbing against the metal. This helps both the wheels and the rails last much longer while reducing noise and friction. Engineers carefully design the shape of both the wheel and the rail to work together. The top surface of the rail is slightly rounded, so it matches the conical profile of the wheel. This allows the wheel to shift gently from side to side, while still maintaining stable contact with the rail. The interaction between these two shapes forms a dynamic system that naturally guides the train forward. Every train axle repeats this process at the same time. A single train may have dozens of wheels working together. each performing tiny corrections as the train moves. These corrections combine to create a stable motion that keeps the entire train aligned with the track. The simplicity of the idea is what makes it so powerful. Instead of relying on complicated steering systems, the railway uses basic geometry and physics. The shape of the wheel alone controls how the train behaves on the track. It turns a heavy mechanical system into a self-balancing structure that constantly guides itself. This design also allows trains to move extremely efficiently. Steel wheels on steel rails create very little rolling resistance compared with rubber tires on asphalt roads. Because friction is low, trains can move large loads using less energy than most other forms of transportation. The wheel design helps maintain this efficiency by minimizing unnecessary contact between the flange and the rail. Across the world, railway systems depend on this same principle. Freight trains carrying thousands of tons of cargo rely on the conical wheel design to stay aligned during long journeys. High-speed passenger trains use the same basic geometry while traveling at remarkable speeds. Even subway trains operating in crowded cities follow the same mechanical rules. The concept has remained largely unchanged for nearly 2 centuries because it works so well. Engineers have improved materials, manufacturing techniques, and track construction over time. But the fundamental shape of the wheel remains the same: a slight cone, a carefully shaped rail, and a small flange waiting as a backup safety guard. Every time a train rolls along the track, this quiet system is active beneath it. Tiny shifts left and right are constantly corrected by differences in wheel diameter. The axle rotates, the wheels roll, and the train remains centered as if guided by an invisible hand. Passengers inside the train rarely think about the physics beneath their feet. They feel the smooth motion of the journey without noticing the constant adjustments happening below. Yet the stability of the entire train depends on that subtle conical shape and the clever interaction between wheel and rail. This combination of geometry, motion, and balance turns a simple wheel into a powerful guiding mechanism. A small change in diameter across the surface of the wheel creates a natural steering effect without moving parts or external control. It transforms the track from a simple pathway into a guiding system that works with the wheels rather than forcing them into place. As the train continues forward, each wheel quietly repeats the same cycle of balance and correction, keeping the massive machine aligned with the rails while it moves across landscapes, cities, mountains, and plains. Great engineering does not always look dramatic. It often hides in quiet details that most people never notice. A train moving across the landscape looks simple from the outside. Steel wheels roll along steel rails, and the journey continues mile after mile without interruption. Yet beneath that calm motion is a small piece of design that carries an enormous responsibility. The shape of a wheel, the slight curve of its surface, and the careful relationship between wheel and rail guide machines that weigh thousands of tons. No steering wheel, no complicated control system constantly correcting the direction. Just geometry and physics working together every second the train moves. A tiny difference in diameter quietly balances the train and keeps it centered on the track. Each wheel adjusts the motion naturally, correcting small shifts before they even become noticeable. It is a system so simple that it almost disappears, yet so powerful that it has guided trains safely across continents for generations. This is the beauty of elegant engineering. The solution does not shout for attention. It works silently in the background, while millions of passengers travel every day without thinking about it. Freight moves across countries, cities stay connected, and entire economies depend on a design that hides in plain sight beneath every train car. A small conical shape, a protective flange waiting as a backup, and a pair of rails stretching toward the horizon. Together they form a system that has shaped transportation for nearly 200 years. Once the idea becomes clear, every passing train tells a different story. What once looked like simple motion now reveals a quiet masterpiece of physics and design, guiding the journey forward. The next time a train rushes past, the sound of the wheels on the rails will carry a deeper meaning. Beneath that sound is a clever piece of engineering, doing its job perfectly, balancing weight, motion, and direction, without anyone needing to guide it. It is a reminder that some of the most powerful technologies in our world are not the loudest or the most complex. They are the ones that work so smoothly that we forget they are even there. If exploring the hidden science behind everyday things sparks your curiosity, then this is the perfect place to keep learning. Every ordinary object around us carries a story of physics, design, and human creativity waiting to be uncovered. So if you enjoyed this journey into the surprising mechanics of trains, take a moment to support the channel. Subscribe to Feynman's Chalkboard so you never miss the next discovery. Like this video if you found it interesting, and share it with someone who loves learning how the world really works. There are countless ideas hiding in plain sight, and together we will continue uncovering the invisible engineering that quietly shapes our everyday lives.